Hello students. Now, through these simulations, let us try to understand the observation made by the Rutherford during his alpha scattering experiment. All the observations which were made by Rutherford, we are going to see through these simulations. So he took an alpha particle and a gold foil, and we can see the observation which the Rutherford would have made that time, that alpha particles are scattering in various directions. Now, mostly alpha particles are passing straight, but some of them are getting bounced back by a small angle. Mostly we are finding them straight, but only some of them will be getting bounced by a small angle. Very small angles, you can see bouncing, it's a very small angles, right? And one more thing you observe, that during experiment, let's see what was the experiments. So here you can see the alpha particles are mostly, they are alpha particle, they are going straight, and only few of them, as he said, get deflected in different directions or get deflected by a small angle. And he also said that 1 in thousands get deflected by 180 degrees. So that means mostly we are saying that these are getting deflected by small angle, but none of them we can see so far getting deflected by a 180-degree angle. So that means observations of the Rutherford was that from his model of an atom, after his experiment only, he gave a Rutherford model of an atom, right? So in this, we have observed. But after the structure of atom, which Rutherford gave, has certain limitations. So another structure of atom was proposed by Niels Bohr. And what was his structure of atom? He said that electrons are revolving in an orbit. As you can see, the electrons revolving in an orbit around the nucleus. Then he said there are only certain specific orbits which an electron can revolve. Now, why he said so? He said that angular momentum should be integral multiple of h by 2 pi. Why he said so? If you try to recollect the lesson, dual nature of radiation and matter, and in which it was said that matter, while moving, can behave as a wave. So now this electron is revolving in an orbit, so it should be behaving like a wave. You can see the wave structure of an electron revolving in an orbit. Now, if the circumference of the orbit should be such that it should be such that the length, or you can say the circumference should be of the length, which should be integral multiple of lambda. Because if a wave is formed, so we cannot say one wave or two wave, we cannot say half wave or 1.5 wave. The circumference of the orbit should be an integral multiple of lambda. And for this reason, Bohr says that only certain specific orbits are allowed. So if electron is in this, next will be 5 in between. If any other orbit is there, electron is not going to stay over there. Next thing says electron in a stationary orbit does not emit radiations. It emits radiations only when it jumps from higher orbit to a lower orbit. So energy according to the difference of the orbit, as we see over here, this energy difference for every orbit. So right now the electron sits in fourth orbit with the energy of 0.8 electron volt. Now, if the electron jumps to the third orbit, then energy should have is 1.5 electron volt. So in that case, it is going to emit the energy radiations and come to the third orbit. Similar manner, if the electrons jumps from lower orbit to higher orbit, so the energy difference between the two orbits will be absorbed and the electron is going to jump to a higher orbit. So based on the emission of energy, and hydrogen spectrum was plotted, and here you can see that when an electron from higher orbit coming to first orbit, the series of line or the wavelength which were recorded was for Lyman series. Coming on to the second means Balmer series, then Paschen series we have, then we have bracket, and we have P-Fund series. So I hope you would have understood the topic now. Thank you, students.